Hello everyone, welcome to the first video going over the book by Shankar. This video will go over the first 3 sections and save the last couple for another video on motion in constant acceleration. So in this video we're just introducing these motion diagrams, position as a function of time, and defining some related quantities, velocity and acceleration and average velocity and acceleration. We'd like to be able to answer this question in the course of the video. For what time in between the initial time and the final time is the velocity equal to the average velocity? So maybe that question doesn't make much sense now, but hopefully it'll be clear by the end of the video. So this is the first video. We just want to get a sense of what this graph is saying. We're studying motion in the first few chapters. So this picture is telling a story. And so the first thing we want to do is understand what this graph is saying. So we're following the motion of an object that starts off at x equals 0. So remember, this is already maybe a little different from what you're used to in a math class, because on the vertical axis is position and the horizontal axis is time. So let me just label these: time and position along an x-axis. Next chapter, when we talk about more than one dimension, we can have several of these graphs, like x-coordinate versus time, and then a separate graph with the y-coordinate versus time. Okay, so this particle is starting off at x equals 0 at this initial time, which we'll call 0. 0 equals t naught. Let's suppose maybe this is 1 second. So in 1 second, what we can read off from this graph is that this particle or object has covered this much distance. If we look to the next second, it looks like the particle is just right here, and they only covered this much distance. So they've slowed down. So if we label this maybe T1 and T2. So from 0 to T1, the object covered more distance than in between time T1 and T2. So just in reading this graph, we see that an object is moving pretty fast at the beginning, and then it slows down, and it looks like they're kind of going at the same speed, right? Between T2 and T3, it looks like they covered the same amount of distance. So they've slowed down by the time they hit T1, and then they remain at that slow speed, and then they start to speed up again. Okay, so this is an important skill to realize what is going on in a graph like this. All right, so if you were to create a story for this, maybe someone is driving on a freeway, and then they hit a town, so they have to slow down from a freeway speed to like 10 miles an hour, and then as they go through the town, then they go back on the freeway. So they speed up back to a freeway speed or something. Right? That would be a story that matches this graph. Okay, so in talking about velocity, you'll hear 2 common things. So average velocity and instantaneous velocity. So I want to talk about some of and this is what Shankar really pins down in section 1.3, average and instantaneous quantities. So I want to contrast these 2 things. So an average velocity requires a time interval. Okay, the speed of a car at any one moment is just whatever the needle on the speedometer is saying, right? So instantaneous velocity is not like average velocity in that this is defined for an instant, requires an instant of time. So this thing on the left, average velocity requires a time interval, instantaneous velocity requires an instant of time. So let's go up right here and talk about, so an interval has already been defined for us. We want to talk about from the initial time to the final time. So we use the subscript naught, NAUGHT for initial quantities, and then we often use F for final quantities. Sometimes you'll see an I for this one, sometimes you'll see nothing for the final one. Okay, so the average velocity, there's a definition. So actually, let me write down the definition first and then point to what it means on the graph. The average velocity, V average, is delta x over delta t. So change in position over change in time. So whenever you see a delta, this triangle in front of a quantity, it means take the final value of that quantity minus the initial value of that quantity. So it's true for the x's and it's true for the times, final minus initial. And remember, this is defined during a time interval, so there is a final and initial. So if someone says average velocity and you don't know what the interval is, then there's a problem. You have to specify what the interval is. Okay, so looks like this is rise over run in a graph of x versus time. So on this plot, what this is if I draw a line, that's pretty good for me for a straight line. The slope of this, so the slope of this line is v average for this particular time interval. So notice how if we picked a different value for the final time, we could get a different slope out of this, right? So the average velocity depends on which two times you choose, what the time interval is. So this v average is delta x over delta t for that particular interval. Now this other thing, instantaneous velocity, is going to be, we're going to have just v without the average. And actually, we're going to be talking about instantaneous velocity more often than average velocity, just in general in the future. So that's why this one doesn't have a subscript. V is the derivative of this function, x is a function of t, with respect to time. Okay, so you might see it written this way. You might see it written derivative with respect to time of this function, x of t. It means the same exact thing. Now, what this means is this is going to be the slope of the tangent line of the graph at any point. Okay, so for any point you look at, so let's just specify this point right here. We can draw the tangent line to the graph, and the slope of the tangent line would be the derivative. Okay, so for this particular time, the slope is the velocity at that point. Okay, so v is dx dt is the slope. Okay, it's bigger right here, and it gets smaller. It seems to reach a minimum somewhere in the middle of this graph, and then it goes up again. Right? But notice how the velocity is defined for a single point in time. So a single instant. It's whatever, so if this is the graph of a car going from a highway speed to slowing down in town, at any instant in time, the needle of the speedometer is pointing at a certain value. Okay, so that value is going to be the speed of the car. And then the velocity is going to be that number and in the positive x direction. So it'll be positive that number. Okay. Get rid of this to clean up the diagram. So I think already we're able to solve this question. For what times is the derivative equal to the average velocity in that time interval? So it looks like, so we need to find the points on the graph where the slope of the tangent line is the same as the secant line. So it looks like maybe right here. So I'm having in mind a line that's parallel to this red one, and just barely grazing the graph, the motion graph. So it looks like that's one of them, and it looks like this is one of them as well. Oops, maybe that's a little too big of a slope, right? Ooh, artistic ability is being tested right here. So it looks like that point in time and this point in time are the two times where the instantaneous velocity is equal to the average velocity. So it looks like it's true for TA and TB. Okay. So the answer would be TA and TB as labeled in the graph above. So only those two instants. Okay, so one other thing about this is that this is the slope. So the average velocity is the slope of the secant line. You might be having nightmare flashbacks from calculus about this. And this is the slope of the tangent line. All right. So these are related but different phenomena, or quantities, sorry. average velocity and instantaneous velocity. Okay, so I want to talk about acceleration now. And I want to note that there's a very similar definition for average acceleration. So there's also A average. So velocity is talking about changes in position over time, right? Whether it's over an interval or at an instant. So velocity is describing changes in position. The next thing is to talk about changes in velocity. So the fact that the car slowed down, there's a quantity that will capture that. So this is not a straight line graph, right? This position versus time. The car slowed down and then it sped up. We have a quantity that can help us with that, and this is called acceleration. So acceleration. So this is actually instantaneous acceleration that I'm going to define here. A is the derivative of velocity with respect to time. And notice I put instantaneous in parentheses because if we just say the word, we mean the instantaneous value. So if someone ever says velocity, they mean instantaneous velocity. You know, if they mean average velocity, they really have to say both those words, average velocity. Okay, so the instantaneous acceleration is defined pretty similarly as velocity is defined to position. So there's instantaneous acceleration, and then there's average acceleration. A average, which is defined over a time interval. So this would be delta V over delta T. Okay, so we have two new definitions of acceleration that we can guess from the definitions of velocity. So Shankar does exactly this. Talks about these two quantities: average velocity, average acceleration, and then notes that, oh look, by the way, instantaneous velocity is the derivative, which is it's like taking average velocity and then shrinking the time goes down to 0. So if you imagine taking these 2 points and shrinking TF to go closer and closer towards T initial, then the slope of the secant line becomes the slope of the tangent line. So Shankar is just reminding you a little bit of some calculus knowledge. And to jump straight from motion to acceleration involves the second derivative. Right? So analyzing motion is a lot like analyzing graphs. All right, so let's try and graph. Okay, so let me do it without copying it right there. Let me repeat the diagram that we had. So x versus time, it looked like this, and then it kind of flattened out, but not totally flat, and then it went up again. Okay, this is x versus time. So from a position versus time graph, you should be able to plot what a velocity versus time graph should look like. V is dx dt. So let's think about this. The slope, so when I talk about the slope of x as a function of time, I mean the slope of the tangent line at a bunch of different points. So for every one of these time values, there's a tangent line that we could draw, and then we could talk about the slope of that value, positive, negative, or 0. And it looks like the slope of all of these, it looks like it's positive, right? Positive here, positive slope here. Even though it's small, it's still positive. It never quite completely flattens out. Right? It's pretty close, but not quite completely flat. So it looks like V of t is always positive for this problem in particular. It looks like it starts off pretty big. Maybe I didn't draw that to scale here. It's supposed to kind of match on the second half what it did in the first half. So let me try and redraw this. Let's see, we start off pretty big, go flat, and then wind up like when we started. Okay, so the slope at the very beginning, so let me draw a few key tangent lines here. One is at the very beginning, it's pretty big, and then in the middle, it's very, very small, but still positive, and then it's pretty big again towards the end. Right? Tangent line right here matches the one at the beginning. Okay, so the slope of those three lines looks like it starts off really big, and then in here it almost flattens out, so it's kind of down here, the value of the velocity is pretty low right there. So I mean, where it crosses, this is the actual value. This is the minimum velocity occurs around those times. And then it comes back up again to here by the time we get to this time. So this graph, I would say it kind of goes down like this, and then it hangs down here a while, and then it starts to go back up again. So from the position versus time graph, we're able to draw the velocity versus time graph just by knowing the fact that it's the derivative. We're drawing the derivative of that graph. So then you can probably guess what we're going to do next. We're going to draw the acceleration versus time. So the acceleration is the derivative of velocity with respect to time. We can do the same exact trick. So now the slope is not always going to be positive, right? It looks like we start off negative. This is a negative slope. And then we do actually hit exactly zero slope, or what is very close to zero slope right here. So for all of these times, we're basically zero slope. And then we get positive slopes again. So we need to capture that fact in our acceleration versus time graph. So the slope is actually relatively constant right here, right? It's negative and roughly constant. So I'm going to start off at some negative value, and it's going to be roughly constant. And then we pretty quickly go to 0. We stay at 0 for a while, and then we go up to that positive slope for a little while longer. It's supposed to be even. This final time value is supposed to be right here or right here. So this is TF in both these cases. And then TF is the final one there. So 3 very different graphs, right? So we started off right away with a negative acceleration, which means that the velocity is decreasing. So notice how the velocity right here is pretty big. This is v max. And then we're going down in value of v, right? We go down from v max to v min. So v is decreasing in quantity, and so therefore the acceleration is negative. And then 0 acceleration while the velocity is constant at v min, and then as it increases, a is positive. Okay. So you'll be getting more practice with this as we do some problems, but this is just kind of a reminder of calculus and drawing derivatives of graphs. Okay, so I want to point out, so one last thing in this video, I want to point out other related formula to the ones we've already written. So the definition, v is defined to be the derivative of x with respect to time. Let's multiply both sides by dt on both sides. And actually, I'm going to write it this way. Derivative of x is v. So dx is equal to v dt. And then I can integrate both sides. So put an integral sign on both of these. Integral. Now we're integrating from one time to another. On the right-hand side, we're integrating over time. So we're going to integrate from some initial time to some final time. On the left, we're integrating x. So at the initial time, there is some x value where the particle originally was, x naught, and then the final position right here. So left-hand side, integral dx is just x evaluated at the endpoints. So we have x final minus x initial is delta x. You should think of integral dx as delta x. Delta x is integral of v dt from initial to some final. Okay, so this quantity, delta x, is called the displacement. Even though distance is just a number, it's just a positive number. Displacements can be positive, negative, or 0. Right? If you walk somewhere, if you walk 10 meters forward and then walk 10 meters backward back to your original spot, your displacement is 0. Your delta x is 0 just because your x final is 0 and your x final is the same as your x initial. That doesn't mean that the distance you traveled was 0, right? But displacement can be 0 even though distance is not 0. So that's displacement, and then similarly, we can get the equation delta v is integral of a dt from t naught to t final. So this is the same exact derivation except using the definition for acceleration as a derivative of velocity. So notice how these are also area under some curves. So this is area under the v of t curve or graph. And this right here is the area under an acceleration versus time graph. So let's look right here. If we took the area right here, so let's look at the relationship between x and v. If we took an area right here, looks like that area is positive. You know, these areas are the sense in which we use them in a calculus class. If the function is above the horizontal axis, then it's a positive area. You know, you're integrating from left to right. So what that means is that from, say, t naught to t, just call it t1. So that area is positive. What that area is exactly the delta x from t naught to t1. So see how t1 you get up to right here, x1, and then you start off at x0. So this is delta x right here. x1 minus x naught. X naught was right at 0 because we started right there. So this value delta x is related to the area under the curve. So see how the area is just a little bit right here? That corresponds to a tiny delta x as we go from t1 to, say, this point right here. Okay. And then a similar relationship holds for the area underneath a of t. I don't want to mess this up too much in this diagram. So this area is related to delta v. And in this case, it's negative because this area is underneath. So if you integrate from left to right, you actually get a negative value for the integral of a dt. And therefore, delta v is negative. You know, the velocity right here minus the velocity right here is negative. So here, delta v is negative. And just to be clear, this is v. We have to be clear about the interval, remember? So v1 minus v0 is negative because the area here is negative. All right. So there's a lot of fun you can have just playing with calculus and these quantities, right? To summarize, you have x of t, you have v of t, and you have a of t. Position, velocity, and acceleration. To go this way, you have to take a derivative. So if you say you have x of t, you take a derivative with respect to time. So with respect to time, and then you get velocity. Take another derivative, you have acceleration. To go the opposite way, you have to integrate. So if you integrate v of t, then you get x. But remember, it's delta x, right? If it's a finite, if it's a definite integral, then you get the displacement delta x. All right?